Hello and welcome again to MECH314, Introduction to Fluid Mechanics. We continue in this part 2 on chapter 2 our talk about the atmospheric pressure. So we found out that the atmospheric pressure had implications, engineering implications and life implications for us humans on the surface of the Earth. And now if we try to look at the atmosphere, this plot is taken from your book, Frank White. Here you have the altitude, so this is 0, the surface of the Earth, and the altitude is measured in kilometers. And here we're looking at the temperature, and in this figure we're looking at the pressure. And you'll see that in the troposphere that the temperature rises from approximately an average surface temperature, that's the air temperature, of around 15 degrees C all the way to about minus 55 degrees C at around 11 kilometers. And then it stays constant for another 10 kilometers, and then does these weird things that have got to do with all kinds of processes within the atmosphere. Remember, this is the within the atmosphere, as well as it's got to do with the sun rays that come in, and with the ionization, and with the distance from the surface of the Earth. But suffice it to say that our atmosphere is pretty much contained within the first 100 kilometers, or maybe 60 to 80 kilometers. And in fact, most of its mass, as measured by the pressure, because the pressure is related to the gravitational pull, is within the first 30 to 40 kilometers. So you look at the pressure distribution, it sort of it has an exponential type or power law type relationship. So let's focus on where we live and where we fly. So within the first 10-15 kilometers of the surface of the Earth. So with the temperature distribution is linear, and if we take this linear temperature distribution, let's try. Our task is to show that in fact the pressure within the atmosphere behaves according to a relationship like a power law. So let's do this exercise. Start with this picture, this linear picture, and produce this picture over here. Okay, so let's get going. So as we said, let's take Z to be the altitude from the surface of the Earth, pointing away from the center of the Earth towards the outer space. We take let's take the surface temperature, for instance, 15 degrees C. The surface, that's the air temperature, and around minus 50 at, let's say, 10 kilometers. That's where airplanes fly normally when they cruise, so around 35,000 feet. So we want to show that this linear profile actually leads to, in temperature, leads to an exponential or a power law relationship in the pressure. And we want, as a homework, to plot it. So let's do that. So we'll start with a linear temperature profile. So we can write the temperature to be in the form of AZ plus B, as you can see here. So T as a function of Z has a slope of A and B. And if you want to have the A and B, you really need to have 2 points in 2 different altitudes where you have the temperature known at those 2 points. For instance, here are 2 points that you can use, and this is basic linear algebra. You can easily get the A and B. Next step is But what is causing the this pressure variation in the atmosphere? Why is it not constant? We know that we live at 100 kilopascal at sea level. Why is it varying? Well, remember that the source of this atmospheric pressure, just like we derived in the hydrostatic pressure, it was associated with the pull of gravity. Just the gravity pulls the solid elements, liquid elements, and gaseous elements alike. So there is no reason that air doesn't get pulled by the gravity of the Earth. So it is really this relationship, the hydrostatic pressure relationship that we found before. The dP/dz is minus ρg, which means as you go higher and higher in altitude, you'd expect the pressure to drop at a slope of ρg. And when we had ρg to be constant, we found that P was equal to minus ρgz plus some constant. Gravity, for all practical purposes, over this 10 kilometer, we're going to take it to be constant, which is fair enough. The density, however, we'd expect it to be varying. So when we rearrange and say dP is minus ρg dz, the density now depends on dz. So we need to find a relationship. We can't just integrate like we've done before. We need to first define a relationship between, we can't take rho constant. We need to find a relationship to replace rho in terms of z. So what do we know? We know that the temperature is a function of z. We know that we have air filling the atmosphere, so if we treat it as an ideal gas, we'd expect there's a relationship between temperature and density, so the density would also depend on the altitude. Now, is it going to be linear like the temperature? We'll see based on the ideal gas law. So if we use the ideal gas relationship, you remember it as PV equal RT, where V is the specific volume. Specific volume is just 1 over density. So we can rearrange the density on one side. The density depends on the pressure. The higher the pressure, the higher the density. And the lower the temperature, the higher the density. So density depends on both pressure and temperature. So let's take this rho, plug it in here. So dP will be minus P over RT gz. R is the gas constant for air, and T is the temperature. So we've replaced them, dP, and then we still have the minus sign. It's associated with us choosing the coordinate system z to be pointing away from the center of the Earth. And then we have a relationship between this temperature T and z that's given to us in the plot to be linear. And depending on the temperatures themselves, we can get the A and B. So let's take this T, plug it back here, and we will get dP is minus P over RAZ plus B times GDZ. Let's see. R is a constant, A is a constant, Z varies, B is a constant, G is a constant, and then we can separate variables, so we can take the P to the other side. So dP over P is equal to minus this term times dz, and then we can easily integrate. So we've taken it to the left-hand side, the pressure, and what do you get? And let's integrate from the surface of the Earth, z equals 0, to any altitude z. At the surface of the Earth, the pressure is atmospheric, and we want to know what the pressure at any altitude is going to be. So what is the integration of 1 over P, or 1 over X, would be the natural logarithm of X, and this thing will be done in a similar way. So you can either use a substitute variable like AZ plus B is equal to Y, and then DZ will be just AY or ADY. or dy over a, if you will. So this is your just elementary calculus integration, and then so this would be now the log of p over p atmosphere. So we implement the limits, we integrate and then implement the limits, and when we integrate that, we are going to get log az plus b, and then when you set, so we've set z equal z here, and here z equals 0, so that's why you get this 0 right over there. And you have log a minus log b, so log c1 minus log c2, so it'll be log c1 over c2. So we'll combine them into one natural logarithm. You still keep the minus sign. So that's, we've divided here by b, so a over b z plus 1. And then we can get rid of the natural logarithm. You take first the multiplier of the natural logarithm, so it will become a power. And then you take the inverse of the natural logarithm, which is the exponent. And you get rid of the ln. So you get p over p atmosphere is equal to that term to the power minus g over ar. Or in other words, you're going to get the pressure varies with 1 over z to the power, to some power, g over ar. And now we have shown that the relationship that we have discussed in the figure, in the pressure figure, actually holds when we do this. And this is just a demonstration to get you a little deeper into what the atmosphere looks like and its composition, at least its pressure contribution, why the pressure varies. It's all the pull of the surface of the mass of the earth on the mass of the air. And also, this is another example of the hydrostatic pressure distribution when you have a non-constant density. When you have a non-constant density, you're not going to get a linear variation of pressure with altitude or depth. You're going to get more like a power law relationship like we have here. And that's because we had a linear dependence of the temperature with altitude plus the ideal gas law. So maybe a different type of relationship, not the ideal gas law, might give us in terms of density and temperature, might give us a different pressure dependence. So now your task is to do an individual homework. So we will talk about that later on in our live WebEx meeting, but the task involves plotting this relationship for different hypothetical planets where the surface temperatures and gravitational acceleration and everything are. So we'll talk about that in the live meeting. So now that we have learned about the atmosphere, there are other implications about its content and how does the atmospheric pressure come about. There is one last thing we want to talk about, because this is also important from an industrial point of view, which is the convention that people use to report pressure. And that's all relative to the atmospheric pressure. So we know that the atmospheric pressure at the surface of the Earth is about 100 kilopascal. And this is really pretty much, this is our, as we have seen in the thermodynamic tables of water, that water boils at sea level at around 100 degrees C, and when you go much higher in altitude, it can boil at a much lower temperature. So that this pressure is the thermodynamic pressure, and this is really the absolute pressure. We refer to it as the absolute pressure. So there is an S missing here, or the absolute pressure scale. But now you go to the gas station and you want to fill your car tire with compressed air, and then you go look at the gauge, and you'll notice that, well, when it's not hooked up to the tire, you're getting so when it's open, when your gauge is open to the atmosphere, it's going to give you zero pressure, and this is the convention that we want to emphasize in this slide. That is, there are industrial conventions. Different industries report pressure in a different way. So as thermodynamic engineers, there's no way about dealing with absolute pressure. So what you see is what you get. It's the absolute pressure. But as practical engineers, people who work with pressure vessels, with tires, with pumps and so on, they deal with what we call gauge pressure. So they already, when they report the pressure, they already subtract the atmospheric pressure from it. So that zero is, in terms of gauge, so that's a zero gauge pressure, and it already has the atmospheric pressure subtracted from the reading. So when you're 10 psi, so what is the atmospheric pressure? Is 100 kilopascal. That's about 15 psi. So when you fill your gas tire with 10 psi, you're filling it with 10 psi above the atmospheric pressure, which means you're really filling it with 25 psi in terms of absolute pressure scale. And there is a different kind of industry which actually deals with pressures that are below the atmospheric, and this is the industry that deals with vacuum pressure, and pretty much all types of fridges, air conditioning systems, refrigeration cycles. At some point in the cycle, they need to work with vacuum pressure, or pressure below the atmospheric, to induce the evaporation of the refrigerant in the evaporator. So if you look at one of those typical pressure gauges for someone who works in the vacuum industry, in the refrigeration industry, you'll see that their gauge will be reading zero when it's open to the atmosphere, and then it can go from minus 30, that's vacuum, all the way to 15 in terms of PSIs. So it can read minus 10. So here, that's not what we're mentioning here, but this is to tell you that we can go below as minus 10. Here it'll be minus 10 psi gauge, and minus 10 psi gauge is what? Minus 10 psi plus equal the absolute pressure minus the 100 kilopascal. So my absolute pressure is 90 kilopascal. So a 90 kilopascal absolute pressure, what would that be in terms of vacuum pressure? So 100 p atmosphere, which is 100, minus the absolute pressure, this guy, the minus, so it's the minus 10 gauge, or in fact 90 absolute, so 100 minus 90. So it's reported as 10 kilopascal or 10 psi vacuum. So a 10 psi, so to summarize, I can report one pressure in 3 different ways. I have this 90 kilopascal absolute pressure. I can write it as 90 kilopascal absolute, or I can write it as minus 10 kilopascal gauge, or I can write it as 10 or plus 10 kilopascal in vacuum. So you just need to be aware of this, these different industrial conventions, and different industries use different systems. But here is a very important caution. Once you stick with one convention of reporting the pressure, stick with it. You can't mix and match. Mixing and matching will induce 100 kilopascal somewhere by error if you're not careful. So you start your problem solving it with gauge pressure, everything should be in gauge. You start with vacuum pressure, everything should be all pressures should be transformed into vacuum convention, into the vacuum convention, and then continue solving. Or you can start with, you can just say, I'm going to deal with all my pressures as you know, in absolute term, convert them all to absolute pressure scale, and continue solving. You're going to be okay. Any one of those conventions, you must get the same answer. It's just a different way of reporting things. So instead of saying someone weighs 100 kilograms, I could say they weigh 200 pounds, or maybe a better example is water solidifies, turns into ice at 0 degrees C, or we could say water solidifies at 32 degrees Fahrenheit. So it's a different way of reporting the temperature. So that's about it. This is how the atmospheric pressure is important to us as engineers, and you need to know whether you're including it in your calculation or whether you're not including it in your calculation. If you're a thermodynamic engineer, you really need to care about it very much so. As people working pressure vessels and vacuum systems, we don't care about it. We try to get it out of the equation. From the very beginning, we report everything without the atmospheric pressure in it by subtracting it. So the next thing in our that we want to cover in this chapter 2 is when we have a surface of an area A, and we have a pressure distribution around that particular surface. So this pressure distribution could be the atmospheric pressure, uniform around it, or this could be a surface that's submerged under the surface of the water, so it has different pressures at different depths. Whichever it is, this top surface that we're talking about has a total area A, and has a pressure distribution on top of that surface. And we are interested in knowing what is the net force that this pressure is going to produce on this surface, and what is the direction of that force, i.e., in other words, what are its three orthogonal components in the I, J, and K vector space, or in the X, Y, Z components of that. What are they for this force? So this brings us back to our previous lecture that you really need now to remember and grasp very well, that pressure acts on a surface in a compressive fashion, so towards the surface, and it's also perpendicular. It's a force per unit area, so it's a force perpendicular to that area, pointing to that area. But now you see our surface here is not flat, so when the pressure is perpendicular on this piece of the area, it points where I'm pointing with the arrow. But if this is the area I'm considering, and I'm interested in the pressure force on this little area here, it will be pointing perpendicular in this direction of motion that I have just prescribed with the mouse. So we, in order for us to approach this problem. One, you have to define a coordinate system, because eventually you want to get the components in the x and y direction, and then you want to take a small length of the surface dl. So this surface, you'll break it into an infinite number of small elemental areas dl, or small areas, so the area being b times dl, the area of this surface, and b being the width into the page. So I'm starting with the assumption that this surface has a width into the page of equal to b, that is constant. And this is the origin with which I measure my x and y. So the point, this surface prescribed by dA or by dl, is located at this x from the origin, and this y coordinate from the origin. So now, if I'm able to find the force due to pressure on this element, I can do the same thing for all the other, for the infinite number of elements on the surface, and then just sum them up. So let's see how we do that. So I have my area dA, and I have my pressure distribution. As we said, pressure acts perpendicular. The pressure force acts perpendicular and compressive towards the surface. So that's our dF. So it's just the multiplication of the pressure at this particular x and y multiplied by the area. And now I want to get the force on the whole surface. The summation, we sum them up, which we call the integration. But be careful that when you're doing this summation, you need to do it as vectors, because the force dF, elemental force, has a magnitude and also has a direction. So you need to include the direction in your calculation. And for you to do the summation vectorially, it's best that you break your force into components. So how do you do this summation, that integration? Is you break it into the I, j, and k unit vector directions. So that's into, or the x, y, and z. So the dF has component in the x and component in the y. So my dF is making an angle theta with the x coordinate system. So I can do a decomposition or projection of the force dF onto the x and y axes. So my dfx, it will be just the dF times cosine theta, and for the y it will be a sine theta, as you have. So my f is equal to its fx component and its fy component. These are the two components of the force which we are after. So the fx, we just sum all the dfx's, because now they don't have a direction. It will be just an algebraic summation, because they're all pointing towards the x direction, whether positive or negative. So the negative tells you the direction. And then let's substitute for dfx with pdA cosine theta. So that's what we've done here, pdA cosine theta. And what is dA? It is b times dl. But how did we go from dl cosine theta to dy? Well, let's look at this triangle. So I've zoomed on this. This is dl. That is length dl. And I can project the length dl onto the x and y axes. So my dy will be dl cosine theta, and the dx will be dl sine theta. So the dl cosine theta, so that's a 90 degree. The dl cosine theta gives me a dy, and vice versa. A dl sine theta gives me a dx, just dx, which is what you have over here. and then you just integrate. So what do we need now to find the values? We need to know what the pressure function as a function of how is the pressure distributed in terms of y and in terms of x. So let's take some special cases. So the first case, a special case that we want to deal with is when the pressure is a constant. So here we set P is constant. So that pressure is a constant, so I take it outside the integral. So I end up with just B times dy. And I'm integrating where? I'm integrating over the whole surface from x1, y1 to x2, y2. For the whole surface, when I integrate the dA of the surface, I'm going to get the area A. But if I integrate the B dy, the B is a constant, so it comes out also. I'm integrating dy. It's just the difference of y between the start point and the end point. I don't care what the surface does, as long as I look at the start point and the end point. If there is no difference in the y, I'm not going to get a net x force. And you can imagine why that might happen. If this is a perfect sine shaped surface, the forces are pointing, if I'm looking at the fx, the forces are pointing towards the surface in this fashion. So on this surface they're pointing to the right, on this surface they're pointing to the left, and on this surface they're pointing again to the right. So, and since it's a uniform pressure magnitude, they will end up cancelling each other. And same thing for the y component of the pressure, it's going to be P times B times delta x. So this delta x, let me just move to a pen. The delta y that I'm talking about, so that we are all on the same page. So here we're back here, P times B times delta y. This is the beginning of the curve, that's y1. That's where it intersects the y-axis. And here, this is my y2. And this is x1. And this is my, I'm going to extend the x-axis. This is my x2. So delta x is all this distance, and delta y is just the distance between those two lines, the vertical distance between those two lines. So it can be hard for some to imagine that this is the case, but the forces cancel out when you have the same y, and we're still talking about a uniform pressure. So now let's move one step up to when we have a more general hydrostatic pressure distribution. So let's look at that at the case where my pressure distribution is hydrostatic, so it varies with the depth. In this case, I'm going, so delta z, I'm going to use the y to be my z in this case. So P is rho g delta y. So that's my depth. So my gravitational vector is in this direction. So you do the same thing, except now P varies with the area, so with the dA. So I can't take it outside, it's not constant. And the dA cosine theta is just your dy times b, times the width into the page. Same story with the fy component. But then let's say you compute the fx and compute the fy. There are two things you can find out. Is the net force, that is the vectorial sum of those two components, so it's the fx squared plus fy squared under the square root, and you have the inclination angle. So this is, let's say I end up with my F net. So I find my Fx like so, and this would be my Fy. So my F net is going to be in this direction, and the inclination angle alpha will depend on the magnitudes of Fx and Fy through the tangent. And the second important point, so that is the line of action. At least the slope of the line, that's not the line of action, I'm sorry. That's the slope of the line of action relative to the x-axis. That gives me the alpha. But is that line of action crossing the x-axis at this location, or at this location? To know where our force acts through, we know that it's inclined at this angle alpha, but to know through which particular point on the surface or through the x-axis, same story because it's a line, is it going through this point or is it going through this point? We now really need to find its the center of pressure, and to find the center of pressure we need to be able to compute the moment of this hydrostatic pressure force around some origin. So here I'm computing the moment around the origin O, the origin of the xy coordinate system, and it'll be just the y dfx. So you integrate the moments from the y component. So here is dfx. It has an action arm or a moment arm equal to y, and the dfy has a moment arm equal to x. So each one has a moment, and you see around the origin the dfx is trying to rotate you counterclockwise, while the dfy is rotating you clockwise, creating a moment of in the clockwise direction. So that's why you get the minus sign. And we're taking here the counterclockwise direction to be positive, moments in that direction to be positive. And then we still haven't gotten to the center of pressure. I think it's in the other slide. So now if my pressure, so again, if my pressure is hydrostatic, it's rho g times delta z, but in this case we said that my delta z is my y, or some delta y, but let's stick with so this could be delta z or delta y. That's my pressure. Then I stick in for the pressure as rho g as the hydrostatic pressure, rho g delta y, and continue my my calculations, the integral. And then I need the shape. Then I need to know what is the distribution, the surface, the shape of the surface, to know what is the distribution along the area of that surface. So the center of pressure would be the point through which, if the net force passes through, it would create zero moment. So now so what we have done is we have computed the moment around some arbitrary point, which is the origin. We have computed the net force. We could easily do that, right, based on these integrals. And now we're going to translate the force, and when you translate a force, you create a moment, you add a moment to it. So let's define the center of pressure to be the point where the hydrostatic pressure force produces zero moment. So that is let me call that my center of pressure CP. The moment due to the hydrostatic pressure force about my center of pressure is going to be 0. And you can, in one way, you can go to the previous equation that talks about the moment and say MCP here. Instead of M around O, you can say M around the center of pressure will be equal to the distance of YCP. So the center of pressure is still an unknown location. And here it's the XCP, that's the coordinate measured from CP, and that would be equal to 0. So this would be a cumbersome equation to solve for. A much easier one is, since you have the pressure distribution, as we said, you find the F net, you find the moment around a known point, so you find it around an arbitrary point, point O. And then you use the magic of your statics course, where you can move a force along a line, but then you add with it the moment associated with the distance that you have moved. So we have the moment around point O, and we have the F net. So if you divide the moment around point O by F net, that's going to give you the distance L. So if you place the distance, if you place the force F net at a distance L from the origin where you computed your moment, you're going to get to the center of pressure right away. So the L perpendicular here is the distance from the origin O to the center of pressure in a perpendicular fashion. So these are really our three relationships that we have come up with, and that we will be using all along to solve problems. We need to get the F net. We need to know that's the net force due to the hydrostatic pressure distribution around the surface. We need to know the inclination angle, and we need to know the location of the center of pressure from the origin of our coordinate system. Great. So that is our hydrostatic pressure distribution, and now we can apply this to any type of surface. So let's take this this problem right over here, and let's start discussing this in the next lecture. So thank you for your attention, and we will continue with this problem in the next lecture.